section 9.5 series.
Hey, this is actually pretty interesting stuff.
Okay, so a sum refers to a finite number of terms being added together.
Right.
Finite means countable, so...
Right. Even if it's like 100 jillion, you
Yeah.
can still, in theory, count to 100 jillion.
Whereas you cannot count to infinity unless you're Chuck Norris, like we discussed in the last
Right.
video.
Right.
So a series refers to a little issue with my grammar there. A series refers to an infinite number of terms being added together. So then you are talking about like...
And that is cool because, believe it or not,
sometimes you can actually find that sum. You'd think if you were adding forever that you would
add
be
up
able
to forever.
Yeah, it would just like go to infinity, but not all of them do. So whenever we're dealing with sums in series, we have this thing called summation notation, which is just one of the coolest phrases ever.
And it's got a sigma. I mean, hello, we can all be frat kids.
Yeah, well, I'm not really a big fan of my own sigmas. That, like, with more practice, you get better at stuff in general. Like, my curly brackets are, well, that's not a good example.
That was a horrible curly bracket.
But, like, that's pretty good.
That's not bad.
I mean, but...
Let's see a sigma.
My sigmas, I mean,
That's
it's
a little
okay.
awkward, but it's not horrible.
But
we can work with it.
Anyway, so, and really you don't even need to, just as long as it looks kind of like a pointy E, we're good. So we use this notation to talk about, like, this right here would be some kind of expression or whatever that...
It would look like our functions look to us right now.
Right, like n squared plus 1 or k minus 3.
Right.
This bottom number, k equals 1, that is where we start.
Yeah, it tells you what number to put in to get your starter.
Yeah, we're to put in first, and then in up here could be a number, or it could be in, or it could be infinity, but it tells you where you're stopping.
Right.
And so we're going to practice in example 1 using summation notation. So
all right, let's do it.
we have here 2 plus 5 plus 8 plus 11, ... plus 29.
Oh, all the way up to 29.
So
okay.
this is stopping at 29. So we are going to have a number on top.
Right.
Our first term is 2, and then it looks like we're adding 3 each time. So that's an arithmetic sequence, which we learned in the last section. So before we actually start with the sum,
we got to get an explicit rule.
Right. So we start with 2, and then after that we add 3 each time, and so we said there was this explicit rule we could use each time. Well, now what we can do is we can think about, well, when I plug in 1, okay, I do get 2, so my sum starts, and you can use k or n or whatever you want.
Sometimes j's or i's will show up. Those are your
K
normal summation.
K and n are really big though.
Right.
And then we can put this in as our like expression.
Right.
But then we got to figure out what number we're ending on for 29. So to do that,
Can't we just set that equal to 29?
Absolutely, and then solve. So you'd subtract 2 over, and I'm going to distribute. Well, you don't have to distribute the 3 actually.
You could,
I could just leave it and then divide by 3.
Right.
So subtract the 2 over and get 27. Divide by 3. My equals. I have trouble here. This is going really badly on the equals sign front. Okay, so add 1 and you get n equals 10. That's the number that goes on top.
That's your stopper.
So we had to figure out for sure where we were starting, because sometimes it makes more sense to start with like a 0.
Right. Sometimes, and you could write this one to start with 0.
You could, and what happens is if you go left a spot on where you're starting, which that's what 0 would do, then where you're ending would go left a spot, and this actually ends up, I think it goes backwards. Like we would put just in there instead of n minus 1, so it's like we're going to the right. It's really, it's something you have to get used to with some practice.
And some of these can be really challenging to discern as well. So it just takes some practice and time. And
yeah. So this is actually really nice that they gave us this information.
Look, they gave us the pattern there.
Yeah, that's the pattern we're going to use. And so we're going to put n plus 1 cubed. And then that means, because that's the last term, that n is where we're stopping.
Right.
And that can be confusing, but basically we're going to plug in all of the numbers until we get to some arbitrary number n.
Some made up number n.
Okay.
Some specific number.
Yeah. And then now we just have to figure out what number we're starting with.
Right.
Instead of what number we're ending with. So we would do the same thing as before. N plus 1 cubed has to equal 1. So what does that mean that n is? Well,
take the cube root of everything.
Cube root of everything, and we still have 1, and then you subtract the 1 over, and so see here n equals 0.
Oh, looky there, it does equal 0.
And I feel like I don't know. Should we have used a different letter than N?
On the top?
On
the bottom?
No, on the bottom. Like typically our indices.
You could still say a K if you want.
And K.
Yeah.
Sorry about that. You having to write over it, but. So we start at K equals 0, we plug into K plus 1 cubed, and then we're going to stop when we get to N.
Right.
And lastly, C. So this one's...
Oh, say, can you see?
This is a geometric series, or series actually, because it's going on through infinity.
All the way to infinity.
And we're multiplying by -3. So let's write our rule for a geometric sequence.
Now pay attention because this alternates from positive to negative.
Right, so it starts with 5, and we're multiplying by -3.
Highway's so good. What's it called, the big country or something?
And then we put an n-1 up here. That's what our
Right.
formula was.
Right.
And so now, if we think about our sum, because it has this ... that means we're going on to infinity.
Right.
So that's pretty nice. And if we think about it, if we plug in 1, we get 0 here, which makes that go away. That is our first term.
Right. So 1 works on this one. I feel like you're having some issues here, Mrs. Stevenson.
I think so. Maybe you may have to write on this one.
I may have to write after this. Nobody wants that.
There, right there.
Beautiful. There you go. All right. So we're going to look at the sum of a finite arithmetic sequence, which is the whole adding and subtracting part.
Yes.
Yeah. Okay. By the way, I've taken over control after the last slide's debacle.
Yeah, it was a little bit of an issue.
So we got A1, A2, A3. These are your terms. The first term, second term, third term, all the way up to that nth term, which is determined by wherever we're told to stop. Okay? And this is finite, so that means that we actually have an actual stopping point with a common difference D, which means every term is different by just the same little teeny tiny amount or whatever. Okay? So here's our formula for that. All right? And this goes back to, was it Charles Frederick Gauss? Was it Gauss? That added up the first 100 numbers. His teacher gave him an assignment and said, look, you need to add up the first 100 numbers. And then after you do that, bring me your, they wrote on slates, bring me your slate and I'll tell you if you got the right answer. Well, he did it very, very quickly. And he discovered actually this pattern right here.
Right.
Okay. So n's the number of terms. First term, last term divided by 2 times the total number of terms.
Right.
So we could very easily add this up and find the finite sum of this problem. Now, we could add up all of these, -8 plus -1 plus 6 plus 13.
And you know, honestly, that's really not that much work,
27.
but we're practicing skills for like when it is more work.
Right. So if we go, hey, from 1 to 1,000.
Yeah.
So we could do it this way, but all we need is the first and last term. So that's going to be -8 plus 27 and divide it by 2.
And then times it by...
And then we need to just know the number of terms. 1, 2, 3, 4, 5, 6.
Yep. And so that's what's in front.
Times 6. And then when you do this math, you're good to go.
Right.
Okay? So 3 times 15, I get 45.
I don't think that's 15.
17? Is it 17?
I'm thinking 19.
Wait,
-8 plus 27? Isn't that 19?
19. That's what I said. 3 times 19, which is not 45.
57.
This is why you should do this kind of stuff. I mess it up all the time. 57. All right, there you go.
Okay, and so we use that middle formula up
Right.
there, and that's handy if you know the first and last and the number.
Right.
If we didn't know the last term, but we knew the number, we'd want to use the last one there, which looks a lot more like
This one right here looks like
that looks like the formula
for an
an
explicit term.
Yeah, with a 2 in front and an n over 2 in front.
Right.
So we could use that if we were given slightly different information.
Right, depending on what we had.
Right.
But both of these guys, if you sort them out, give you the same information.
They do.
So it's pretty interesting stuff. Let's sum a finite geometric sequence.
Okay, geometric sequence. So the other type of sequence. This formula is a little more complicated, and we only have one.
You might even need a calculator with this one because sometimes...
Well, it's just annoying to do the math yourself, even if it is possible to do it. Sometimes it's like, ooh, that's super difficult. I can't do that. But even whenever it's not that bad, it's annoying to have to do. So feel free to have your calculator handy. You do have to have the first term, the common ratio, and the number of terms. You don't have to know the last term in this case.
But you gotta have some of that basic information, which we are given in our problem. Right. So find the sum of the geometric sequence.
Now this could be tricky with the dots, but we'll actually see that they helped us out. So
what?
Go ahead.
They helped us?
They helped us.
Okay, so if I go to from 4, okay, first term is, so A1 is 4. So we've got that guy all sorted out, no problem. Now I just need R.
Okay. I'm multiplying
by, looks like from 4 to negative 4/3, I'm going to say R is negative 1/3.
I feel like I may have put a typo in there.
Because
I skipped a term.
This should be plus, right?
No, I think I skipped a term. I think there should be a 4/9.
Oh, yeah. There should be a 4/9 in there. So plus 4/9, and then minus 4/27.
Yeah, sorry about that, guys.
That's okay. So we've got this set up, and hey, look, I've got 2 of the 3 pieces. The third piece is right there. So n is 10. Okay,
so if we go ahead.
Okay, so what I'm going to do is just plug these bad boys into the formula that I was given, which would give us 4 times 1 minus negative 1/3 to the 10th power, all over 1 minus 1/3. Now, I know this looks really, really strange and wacky, but it actually will sum up what's going on right here. It'll sum up those 10 terms. So as soon as Mrs. K. Steve, this is usually me. We're backwards right now, so we're both in uncomfortable territory.
This is super uncomfortable.
That's really interesting. So okay, so 118,096 divided by 19683.
Yes. Or if you change that to a decimal, you would get something that rounds up to 6 pretty nicely.
5.99.
9999. I mean, 989.
So almost rounds up to 6 there.
That's interesting. So even though we added a whole bunch of things together and we started at 4, we were only getting to 6. Huh. I wonder what would happen if we kept adding things to it.
I don't know. Well, can we just try real quick what it might be if we just put 100 terms in, just for kicks and giggles?
I'll just go up in
Let's keep all of this the same, and now let's, instead of doing 10, let's do 100. So it would be the same setup.
Just changing the 10 to 100. Wow, that's a crazy looking fraction there. But
holy jeez.
Now, on my Inspire here, it just literally rounded that up to 6. It thinks that if you put in 100 there for that exponent, it thinks this is 6. So that's what we're about to talk about in the next slide, is that we have these series sometimes or we can have a series, something that goes infinitely many terms, and we can add them up and get an actual number. So
I'm excited to see what that's going to look like.
Me too. Example 4. No, we said it too soon. We're not quite to the infinite thing yet. All right, so find the sum of the first in terms of the sequence. The sequence is either arithmetic or geometric. So it's arithmetic if you add the same thing each time.
Geometric if you multiply the same thing each time.
So this first one, 14.
Also, 8, 2, a dead clue giveaway between arithmetic and geometric. If you have alternating signs,
gotta be geometric.
Gotta be. Okay. I'm looking at the first guy go from 14 to 8 to 2. I'm saying D is 6.
Wouldn't that be a negative 6 because we're going down?
That would be a negative 6. Okay. D for down, yes.
So
and so first term, last term. Uh-oh, there's no last term.
There's no last term. So we're going to have to use that other formula.
The other formula.
So we have n is 9. So 9 over 2.
N equals 9. So we're going to have 9 over 2. Whoops.
That's a Freudian slip there.
9 over 2.
And then in parentheses, and then it was
I got the first term, right?
2 times the first term, right?
2 times the first term. Plus. And then it was
like n minus 1 times D.
Which is 9. So 9 minus 1 times D, which is negative 6. Because I need to know how many negative 6s I'm adding.
Right. Why don't you do that on the calculator real quick? I'll be right back.
Okay, I'll do this on the calculator real quick while Mrs. Stevenson runs off. And was that it? Did you just waste a jelly bean?
Nope.
Okay, just checking.
Just delete it, right?
Yeah, 5-second rule. I got negative 90 when I add those up.
Okay, I felt really iffy about that 2 being there. I thought it was just kind of weird, but it's supposed
That's
to be
right,
there.
right?
Yeah, so
okay.
negative 90. And now part B, we have a geometric sequence.
This is geometric.
So now what are we multiplying by each time?
Okay, so I think we're multiplying by a negative 1/2 each time. So
I agree.
I'm going to say r is equal to negative 1/2. And why do I say that? Because I go from 6 to 3. That's
a half.
That's a half.
You
and I go
divide
from
by 2.
positive to negative. That's
a negative.
That's a negative half. So now I need n, which is the number of terms, which is 11.
Yeah.
And I need the first term, which in this case is
6.
So let me change up colors here because you're really good at doing that, and not so much. Okay, so now for the formula part.
We got A1 on top.
So you've got to have your first term,
which is 6.
Okay, and then what?
And then in parentheses you got 1 minus r.
1 minus r to the nth power.
Right.
Right. So my r is 1/2 negative. The n term is 11.
Yeah.
And that's all going to be over what? What was it?
1 minus
1 minus
r.
1 minus r. Ooh, 1 minus r. So that's going to be a positive 1/2 on the bottom. What do you get when you punch it in, Mrs. Casey?
2049 over 512.
Hey, can you decimal that out real quick, just for kicksies and grinsies?
That's really close to 4.
Whoa, mama. So 4.00. I'm going to go ahead and write this out so you can see 195. Okay? And so I have a theory about that purple one. I think it might be 4 if we go to infinity.
It could be. So you want me to try to...
Just check 100 real quick, and let's see if this will give us maybe something to talk about in a minute.
Again.
Ooh, that's a biggie.
4. That's
wow.
Headed towards 4.
Wow.
Now notice we didn't do that. We didn't talk about that with A, because if we plug in a bigger number, because we started with 14, we're just going to get more and more negative. The more negative 6s we add, that's going towards negative infinity.
But if I'm only adding a half...
You mean multiplying by a half?
Yeah, if I'm only multiplying by a half, that means I'm getting smaller every time.
Yeah, what I'm adding each time is getting smaller, so that's headed towards something. Hey, definition of an infinite series. It's a series that goes on for infinity.
What?
Sometimes it's useful to look at partial sums, adding a finite number of terms together of an infinite series. And we're going to do that in just a second, because when I first saw the word partial sums, I was like, what are they
That
talking
sounds
about?
like calculus.
Yeah, it kind of does, actually. So just to go over this definition, we've been hinting at it, and it's kind of like what we talked about last time with sequences, but a series is said to converge if its sequence of partial sums approach a number. So in other words, as you add more and more terms together, the sum should get closer and closer to a certain number.
So go back to the previous 2 slides when we looked at the geometric sequences of those 2 problems.
Right.
And we added an infinite, we added a finite number of terms, just like 100 in each case.
Right, and we were getting really close to a certain number.
And the error on the calculator told us that the answer was 4
right.
on one of them, and gave us a
6 on the
and it gave us specifically gave us those numbers.
Yeah. Okay, so a series is said to diverge if, as terms are added, the sum approaches infinity or alternates between 2 numbers. And when we talk about convergence, like we mentioned, it has to be geometric, and we're actually going to, I think, in a second, see a specific thing that has to happen in order for it to be geometric, which you might actually be able to guess if you haven't already.
Just like the books, everybody dies at the end. Okay, divergent.
Please don't listen to him. Example 5, looking at limits of partial sums. So for each series, we're going to find the first 5 terms in the sequence of partial sums. So the first thing you do is just take the first term, and that's your first partial sum. So you're taking the sum of the first 1 term. Okay, and then you say, okay, what about the sum of the first 2 terms? So if I add 0.1 and 0.01 together, I get...
0.11.
Okay, so...
What are you doing? Why are you taking over?
We're making a sequence of...
Did you not like the way that I wrote that?
Okay, so the first partial sum is 0.1. The second one, we're adding the first 2 terms together, so it would be 0.11. We're making
How did your handwriting get so much better?
I don't know. We're making a sequence of partial sums. So the first one is 0.1. The second one is 0.11.
Can I talk? The next one's going to be 0.111.
Okay.
Thank you. Don't make me ruin the books.
Okay. Next.
0.1111.
Okay. And then...
0.11111.
And that's it. That's all we need. First 5 terms in the sequence of partial sums. So what do we think it is converging to?
I think it's converging to 0.1 repeating.
I agree. So it converges to 0.1 repeating. So
we could get that as a fraction too, could we not?
Probably, but we're actually going to do that in a second. I think it'd be like 1/9 though.
I think you're right. I'll double check.
Try that? Okay, so part B. So the first partial sum is just 10. The second partial sum is 10 plus 20. So the sum of the first two terms, so that's 30. The next one is 10 plus 20 plus 30, which gives us 60. And then 10 plus 20 plus 30 plus 40, so that's 100. And then it doesn't give us the next term, but that would be 50, so that would be 150. So this one is diverging because
it's getting bigger all the time.
Yeah, we're getting closer and closer to infinity. And last, let's try C. Ooh. Okay, so the sum of the first term is 1. The sum of the first two terms, 1 minus 1, 0. The sum of the first three terms,
-1.
No.
0.
No.
1.
1 minus 1 is 0. Plus 1 is 1.
That's what I said.
Okay. And the first four terms,
-1.
0.
I know. Dang it.
And then the next term after -1 would be a positive 1. So that would make it be 1 again. So you might be like, oh, it converges to 0 sometimes and it converges to 1 sometimes. Well, it can't do that.
That doesn't converge. It's got to actually approach one set specific number.
Right. So that diverges.
Where everybody dies in the end. So on this that would be an oscillating situation.
Yes, this
by
is
the way,
oscillating
vocabulary.
when it goes back and forth. And
yes.
So it all depends on where you end your sum as to what value you get at the end.
Right.
You can't be like, oh, until it gets to infinity, this is what the answer is.
Right. So you first.
No, you.
Okay.
Go ahead.
All right. So let's sum up these puppies.
Okay, so here's the thing we've been hinting at this whole time.
The whole time.
If you have a geometric series, which by the way has this form, an infinite geometric series.
It's got to be infinite.
It converges if and only if the absolute value of r is less than 1. So
now it could still be 0.99999.
But that's less than 1.
Less than 1.
And if it's negative, they're saying that's okay, as long as basically we have a fraction that is like an actual fraction, not like 3/2. That's bigger than 1.
That's bigger than 1.
A fraction that's less than 1. If that's what happens, then the sum converges, and
it converges to that right there.
A over 1 minus r, and this is A1 and A1. I don't really like how the book kind of drops out the A1 thing, but it's whatever. So let's do some, right? Example 6. Determine whether the series converges. If it converges, give the sum. So one thing you're trying to look at is this even like a geometric sequence? Like, here we have something that looks exactly like this.
I mean, freaking identical.
Where r is 0.75.
3/4 maybe, if you want to go that way.
If you wanted to, and that is less than 1, so this does converge. We can figure out where it converges by doing a, which is 3, over 1 minus r, which is 0.75.
I'm on it right now.
I think it's 12.
3 divided by 1 minus, what's 5? It's 12.
Bam.
You're so good. It's like you're getting a master's in mathematics.
Converges to 12. All right, so here, you might be like, oh, this looks a little different.
I still say we can do that one.
Because
we can get a first term.
When you subtract 1 from this, you add 1, like they're backwards, and so that still works out.
Right.
That's still okay. And so it is negative, but that's okay. So we should have, since it doesn't tell us, that's a 1 in front, right? 1 over 1 minus a -4/5.
We could also find the first term, right? We could just put 0 in for n.
Oh, you could, yeah.
I mean,
and then that'd
it's
be
going to be 1.
Yeah,
so.
that's true.
Okay, so I'm on it right now. 1 divided by 1 minus -4/5. 5/9. But how did you get that already?
I just showed off. It's okay.
Man.
All right, so
You're brilliant.
this one, okay, looks like kind of a combination of these, but before we even worry about if the n equals 1 and the n is okay, check this out. Pi over 2 is like 1.7.
Okay, I'll just punch that one in there. Pi divided by 2.
1.67, something.
1.5707963267
And so that is bigger than 1, so this diverges. It's not going to go towards a certain number.
Pi over 4, though, would work, right?
Yeah, it would. Pi over 4 would work, and then we would have to go on with that. This one right here is not written in summation notation, which is a little annoying. But we can still find A and R.
We got a first term, though.
And we can figure, because, A1 is 1, and then R is, what are we multiplying by each time?
It looks like a half. Looks like a positive half, even.
And so that is something that should converge, and we can just plug it in.
I like how you're thinking. So 1 divided by 1.
I bet you can do this without the calculator.
Okay, hold on.
No, do it without the calculator.
No, what are you doing?
Do it without the calculator. Come on, use your math. Use
3
your math.
halves?
Okay, I forgot, because I thought about it. And no, it's not 3 halves.
2.
Yes, 2.
Oh, thank goodness.
Okay.
2 guesses every time.
At least.